Okay, so we've been talking about chapter 13, I think. So we've talked about acids and bases, I think, last time, and we did a bunch of sort of calculations and stuff. We talked about I think Kw, right? Which is concentration of H plus times concentration of OH minus, and that equals 1 times 10 to the minus 14. We could use Kw, right, to calculate either the H plus concentration or the OH minus concentration, and we could compare those two to figure out whether or not a solution is acidic, basic, or neutral. Clearly, if the H plus, which is the acid part of the solution, is larger than the OH minus, we're going to have an acidic solution. If they are equal, we will have a neutral solution. And if the OH minus is larger than the H plus concentration, then we'll have basic. We talked about the pH scale and how to calculate pH. pH is equal to minus the log or negative log of the H plus concentration. We have a similar scale that looks at pOH, which is minus the log of the OH minus concentration. And the nice thing about those two things is if you take the pH plus the pOH, that will equal 14. So as we talked about, it does give you a little bit of variety in terms of how you could solve these problems. Remember, though, that it is the pH scale that you probably want to think about. Less than 7 is acidic. Above 7, there's basic. And 7 is going to be our neutral in that case. Remember that, again, that there is only sort of one answer, as we talked about, for that question of is it acidic, basic, or neutral? And again, most people have that pH scale in their head, so that's probably what you should always look at. The pOH scale does run opposite of the pH scale. So if you have a high pH, you have a low pOH, and vice versa, as they run basically opposites of each other. And that's because the concentration of H plus and OH minus also run opposites of each other. So as one goes up, the other goes down, and vice versa as well. We also talked about that you can get the H plus concentration directly from the pH, and that would be our inverse log of the negative pH. Again, on most people's calculators, as we talked about, that's going to be a 10 and a caret. Usually will pop up on your calculator when you do that. You could also do that with the pOH if you happen to have that. You could get the OH minus concentration directly from that by taking the inverse log of the negative pOH, which once again does put our caret up there. We also talked about our calculators again. If you have a display calculator, you do punch it in exactly the way the formula is written. If you have a non-display calculator, as we talked about, you kind of have to go backwards in all these formulas, kind of start with a number and kind of work your way backwards. Any questions on any of those there that we talked about last time? Okay. So I think that is not where we left off. I think I'm way too far back. So I'm trying to find where we're at here. I'll go there. All right, so I think this is where we left off. We did those examples where we calculated everything, I think, last time. Talk a little about electrolytes and a reminder of what electrolytes are, and again, how they do relate to sort of acids and bases. An electrolyte is something that, when dissolved in solution, will basically generate ions, and the presence of these ions will conduct electricity. Strong electrolytes will 100% dissociate in solution, which means pretty much it's just all going to fall apart. And the only thing you have flying around or floating around in that solution are going to be those ions, which is why they are a strong electrolyte, because they will create a lot of ions really fast. So if you had something like sodium chloride, which is a strong electrolyte, 100% of what you would have in that solution floating around would be sodium ions and chloride ions. You would have none of the sodium chloride units basically still together. Now, that's different than a weak electrolyte. A weak electrolyte will mainly stay together. but will break apart a little bit into ions. So it will produce a little of these guys, but it will mainly stay together, and that is our friend acetic acid from vinegar. So when something like acetic acid goes for a swim, it's pretty much going to stay together as kind of the whole sort of unit, if you will, but it will break apart a little bit into some acetate and some H plus ions basically floating around as well. That's why we have these reversible arrows in a weak electrolyte. It goes in both directions, but mainly stays there on the reactant side in this situation. Now, strong acids are strong electrolytes, which means they 100% break apart into ions in solution. There is sort of a good list of strong acids, which are kind of good to know. And these are a lot of them there, like hydrochloric acid, nitric acid, perchloric acid, sulfuric acid, hydrobromic acid, and hydroiodic acid. These are kind of a list of 6 really strong acids, which means when they do go into solution, they're going to completely break apart. So in this case here, going to donate in all these cases are H plus over, and that's going to give us H3O plus in this case, since we do have the water included in the equation, and Cl minus. That would give us H3O plus and a little nitrate, a little H3O plus, and some perchlorate, a little H3O plus, a little HSO4 minus. So 100% of these guys are going to break apart, and this is really why they are all strong acids, because pretty much all they have to do is go for a swim, and you're going to produce a lot of H plus really, really quickly. And that's sort of the definition of an acid, right? Something has the ability to produce H plus or H3O plus in solution. So if you took, again, some hydrochloric acid in solution, basically you will have a ton of H pluses and Cl minuses floating around. Once again, none of the HCl units will still be together. This again will produce a lot of H plus very, very quickly, and you will have probably an acidic solution in that particular case. Those strong acids, again, are good to know because, frankly, if it's not one of those strong acids, it's probably going to be a weak acid. So that's a good way to remember or sort of figure that out. Weak acids, on the other hand, again, are weak electrolytes, which means they will mainly stay together. So our HF here will break apart a little bit into H3O plus and F minus. And now our H3O plus and NO2 minus, our H3O plus and our SO4 2 minus, and obviously here our H3O plus and our hydroxide in this case. So unlike this, pretty much this is what you're going to have in solution if you have one of these weak acids. So just like acetic acid, if you had HF, you're pretty much going to have a majority of these HF guys still together, but will break apart a little bit and produce a little bit of H plus and F minus. Since it's able to still produce a little bit of that H plus, it is still considered an acid, but it's not going to produce anywhere near the extent of H plus that something like hydrochloric acid will do. It basically just needs to go for a swim, that hydrochloric acid, is going to break apart. Now, strong bases are also strong electrolytes, and for the most part, strong bases usually will contain hydroxide. And again, they do come from kind of group 1 and group 2 on the periodic table, which are our alkali metals, our alkaline earth metals. As we talked about a couple of times, I think before, the word alkaline means basic. And if you kind of look at the periodic table there, kind of go like a little lithium, a little sodium, a little potassium, hang it right there to calcium, strontium, and sort of barium, this kind of move. Any of those guys with hydroxide in it, pretty much going to be a strong base. So those are kind of like a lot of your strong bases there. And they will also 100% break apart in solution. None of it's going to stay together. So if you had a solution of sodium hydroxide, you would have a bunch of sodium ions floating around. and you would have a bunch of hydroxide ions freely floating around. And once again, that's going to generate a big amount of hydroxide in that solution really quickly, which means, as we talked about, the H plus concentration in that solution will then drop, right? Because you just increase the OH minus concentration, the H plus comes down, and we would expect it to obviously be a basic solution. There are weak bases, and weak bases will basically accept an H plus going this way. And in this case, water would act actually as the acid in the Bronsted-Lowry definition, and it will produce something like HF and hydroxide. This will produce HNO2 and hydroxide. So once again, they're going to be able to produce some hydroxide in that solution, which would make them a base. So a couple of important sort of relationships between acids, bases, and their conjugate partners, which is really important. We do have H3O plus as the strongest acid we could have, or OH minus, sort of strongest base because it exists in a solution. But the relationship between an acid, for example, and its conjugate base, or a base and its conjugate acid, it's an opposite sort of relationship. So what that means is, if you have a strong acid, its conjugate base will be considered relatively weak. So it's sort of an opposite relationship. So HCl is a strong acid. Its conjugate base, which is Cl minus, will be relatively weak. If you have a weak acid, its conjugate partner will be relatively strong. So sort of a opposite relationship between those things. So when we talk about something being strong in this sort of application, it is not as strong as a strong base, but what it means is, and as we will talk about later on in this chapter, that conjugate base has the ability to continue to react with water that's present in a reaction known as a hydrolysis reaction. So if you have something that comes from a weak acid or even a weak base, what happens is that conjugate partner has the ability to continue to react with water, which is in the solution to begin with, and that can have an effect on the pH of that particular solution. Same thing with the base. If you have something that comes from a strong base, its conjugate acid will be relatively weak, which again, in this sort of context, means weak for each of these things. It pretty much will not continue to react with water. So it's just going to kind of hang out there. It's not going to really do anything with the water. And if we have a weak base, its conjugate partner will be relatively strong. So again, in this sort of context, as we'll talk about a little bit later on, these guys mean that they will continue to react with water and can affect the pH of the solution because of that. So we'll talk a little about that when we talk about salts as we go through this chapter. Any questions on that there? So here's a table. You have a similar one in your book, some strong acids and some bases. Again, here's sort of our strong acid source at the top here. And we see that their partners are relatively weak, stronger bases down here, weaker acids over there. So again, sort of a opposite relationship that is occurring. All right. So why don't you try this? Calculate the pH here of each of these solutions. We have nitric acid, which is a strong acid. And we got a little barium hydroxide, which is a strong base. So what would be the pH of each of these solutions? So see what you come up with here. Okay, so let's take a look. So in this case, we have nitric acid, which is a strong acid. And again, this is not sort of a generic H plus concentration or OH minus concentration. They actually gave us an actual form of an acid. So we know that's a strong acid. We know we want to calculate the pH, which is negative log of the H plus concentration. So clearly here we do need the H plus concentration. So knowing that this is a strong acid, we know that when it is in solution, it's going to 100% break apart into H plus and nitrate in this case. And since we do know the concentration of this is 2 times 10 to the minus 3 molar, we can get the concentration of H plus from that. As you might remember, maybe from 200A, it is a 1-to-1 relationship between those two, which means the concentration here would also be 2 times 10 to the minus 3 molar. By the way, it's also a 1-to-1 relationship between that and the nitrate, which means the concentration of nitrate would also be 2 times 10 to the minus 3 molar, although we do not need it here. In case you're not sure how that works, let me just show you the long part of the calculation there. 2 times 10 to the minus 3 moles per liter of nitric acid. We do a little stoichiometry. For every 1 mole of nitric acid, we get 1 mole of H plus. Moles of nitric acid cancel. We end up with 2 times 10 to the minus 3 moles per liter of H plus. So that is how we get it in that particular case. The quick way is you multiply it by the coefficient you have in front of the H plus or the NO3 minus. This is the coefficient is 1. It's 1 times the concentration of the whole thing. That is how concentrations work. Yes. Any questions on that? So in this case, that's really all we need to calculate the pH in this case. So we can go right into our equation minus the log of 2 times 10 to the minus 3. Again, make sure you punch that in correctly depending on your calculator you got going on. And we will end up with a pH of 2.7, and that definitely is acidic in this case, which we would hope so, since this is nitric acid, which is a strong acid. Any questions on that one there? Now, when we look at this one, which is barium hydroxide, which is a strong base, in this particular case, we would have this guy breaking apart into a barium ion and actually 2 hydroxide ions here. In this particular case, because it is a base, we cannot calculate the pH directly, right? Because we don't have the H plus concentration, but we can figure out the OH minus concentration, which would allow us to calculate the POH first. And then once we have the POH, we could get to the pH probably by subtracting 14 is the easiest move in that particular case. Here we do want to get the concentration of the hydroxide, which is 1.8 times 10 to the minus 2. In this case, it's a 1-to-2 relationship, which means you actually do need to multiply that concentration by 2 to get the correct concentration of hydroxide in the solution. It's basically the same sort of mole to mole relationship thing we were just talking about. 2 times 1.8 to the minus 2.036 molar. And that's going to be our hydroxide concentration. Now that we have that, we can go into our POH, which obviously I wrote wrong here. It should be the OH minus concentration there. And we will do our POH is equal to negative log of the OH minus concentration, 0.036. So we'll do a little bit of that. And that's going to give us a 1.44. A reminder that if for some reason you thought that that was the pH, it should not make sense to you because this is a base. And if that was a pH, that's a acidic pH, right? So that is not the pH, but the POH. Probably the easiest thing to do would take the pH plus the POH, which equals 14 at this point. That means the pH would equal 14 minus 1.44. And we'll do a little minus 14 action there, 1256. That definitely is a basic pH. Any questions on that one? So occasionally you may come across an actual formula rather than just a generic H plus or OH minus concentration. And again, if it's one of those strong acids, it's pretty much going to be your H plus concentration that you need for the pH. If it's a strong base, most of the time that'll be your hydroxide, but I would say probably more so in the bases that are strong, you might have to do this adjustment here for the hydroxide concentration. Yeah.
For the strong bases, are we normally stoichiometry?
What's that?
So for the second equation,
Yeah.
it's a strong base. I just did my
Yeah.
Can I consistently do that, or is there a time perhaps I'll have to use the ice formula?
For these are strong. So these are both strong. So you want us to do anything with the ice because the ice is really for things that are weak. So definitely these, both of these cases here, the acid that's strong or the base that's strong, you really just need to make sure you get the correct H plus concentration or OH minus concentration out of it. And that's pretty much all you need to do with these guys. So the main thing probably would be with, again, the base. You might have to do that adjustment, but if it's a group 1 sort of base like sodium hydroxide, potassium hydroxide, that will be the hydroxide concentration. So, yeah. Other questions? Okay. Then let's talk about actually your question just here in just a second. But here's a table of, again, some of those strong acids, which is good ones to know. Because again, if it's not one of those, it's probably a pretty safe bet it's going to be a weak acid. So, I would invest the time to know these 6. Like I said, it just kind of makes it a little bit easier to go, okay, it's not one of those 6, then it's probably, I need to treat it as a weak acid and stuff like that. And there's, again, some of our strong bases, which is sort of down, over, and then down there in group 1 and 2 on the periodic table. So let's talk about what happens when we are not dealing with a strong acid or really even a strong base, and what happens with weak acids. So weak acid, and this is sort of a generic formula for an acid, HA. Remember that H plus is the cation for all acids. And in this case, this would be A minus, which would be our anion. That would be a monoprotic acid, which has 1 hydrogen basically to give. When we have an acid like this, it will set up an equilibrium because that acid is a weak acid, which means if it can set up an equilibrium, then our favorite thing could happen. We could write a K expression for it. Dare I say this one's going to be called Ka for acid, I'm going to go with in this case. So this is a equilibrium constant for acids. It works the same way. We do our products over our reactants. I would say most of the time I would probably write the equation like this. But once again, if you did write the equation like this with the water there on this side, that's okay, but just like normal, we should not include the water in the equilibrium expression. So, your alternative to this would be the Ka is equal to H3O plus times A minus divided by HA. Again, you would not want to include the water like normal. So a Ka value is an equilibrium constant added to our ever-growing list of Ks. We got KC, KP, KW, KA at this point. We'll still be adding as we go through these chapters here. As the Ka goes up, so does the strength of the weak acids. So let's talk a little bit about that. What that means is as the Ka value goes up, that means we have a larger Ka value. And when I have a large Ka value, do I mainly have reactants or products? Larger K values mean you mainly have products. And in the case of a weak acid on the product side, that would mean I would have more H plus that's free in the solution. And that is why it will be a stronger weak acid. Yeah. So it is still way weaker than any strong acid. But in comparing a weak acid from one to the next, or comparing 2 weak acids together, the one with the larger Ka value would be the stronger acid because it would be able to release more free H plus in the solution. And that's really the definition of an acid, is the ability to release that H plus freely into the solution. Would I find a Ka value for a strong acid? The answer is no, you would not find an Ka value for a strong acid because a strong acid, like say hydrochloric acid, is going to completely break apart into this, which means you have none of that, which means there is no equilibrium, right? So with a strong acid, they do not set up an equilibrium, which means you do not have a Ka value for those things. That is also a very big flag of, I see a Ka value. I know this guy is a weak acid. Yeah, so that's a really easy thing to remember as well. You will not have a Ka value for anything that's strong. For example, the only one that you might get close to is sulfuric acid because it's a diprotic acid. But usually when you look up that value in the Ka table for H2SO4, it'll say very large, which is not very helpful in terms of if you want to do some type of calculation. The reason it's in the table is because it's a diprotic acid and it can release that second hydrogen, which actually is a weak acid. That HSO4 minus is a weak acid. So we typically do not see Ka values for anything that is a strong acid because it will completely break apart. So again, that's another way, and people often have this question of, how do I maybe know it's a weak acid versus a strong acid? Remembering those 6 is a good way to know that they're strong acids. But again, if you see a Ka value, it's going to be definitely a weak acid. A weak acid sets up an equilibrium, which means to solve these type of problems, we need to use an ice table. So this is the situation where you would need to use an ice table. And we would do the ice table the exact same way as we normally would do an ice table. So we would start with our equation. We would have our change in our equilibrium. We would have our initial concentrations. You might have some zeros here. Do a little minus x's, plus x's, plus x's. When you get down to equilibrium, initial minus x, x, and x, just like we would normally do, right? The goal here is to solve for x. We would go into our Ka expression with everybody that's here and solve for x, right? In this case, the main difference between, say, a Ka problem and an equilibrium problem that we did, say, in the last chapter is, in most cases, we're interested in the pH of the solution. So in most cases, we're interested in the pH, which means in a lot of cases, really the only thing we're actually interested in from this ice table is this guy right here. So we're interested in what its concentration is at equilibrium, which oftentimes is what the X value is. And the additional thing that we do is, instead of a lot of times calculating everybody's concentration at equilibrium, we slap it into the pH equation and we get the pH value for that particular solution. So the ice table works the same way as it did in the previous chapter, which means if you have a perfect square, you could do that. If you want to do the quadratic, you could do that. You could also do the assumption as well, if that's possible to do in this situation. And you will solve it one of those 3 ways. And really, in most cases, you're just going to get that X value, which is usually your H plus concentration, and pop it into your pH equation and get the pH of the solution. So although it may look different, may have a different letter, when we talk about Kc, Kp, Kw, Ka, B, Sp, F, all these things, they're all the same thing. They're all really just equilibrium constants, and they all can be solved through ice tables. It's just slightly different things that you do with sort of the information at the end. And these type of problems, we're usually interested in pH rather than concentration. Although sometimes we are still interested in concentrations. So sometimes you'll still go back in and solve for those things. Any questions on that there?